Hey there! Picking up right where we left off. In this lecture, we'll explore how to use NumPy's where function to substitute values within an array. To be more precise, we'll see how to apply the function to switch out the temporary filler values we put in place in the last lecture. Note that what we have done is to create an array where all values are numeric. All missing values are greater than the maximum of this array. This is very easy and convenient for us. If a value is equal to the maximum of the array, it is actually a missing value. In this lesson, we will explore how to replace these values with more meaningful ones. One of the most common approaches is to fill all missing values with the mean of the given column. The reason is that, quite possibly, this won't change the overall interpretation of the dataset. All missing values would be considered average, thus unimportant for the consequent analysis. Note that this is not always valid, but often is the preferred approach. We'll start by loading and displaying the dataset we'll be working with. Then, in a new cell, we'll create a variable called temporary mean and set it equal to the NaN mean function. In the parentheses, we'll pass the dataset as an input and set the axis equal to 0. This ensures we're storing the means for each column as opposed to every row. Now, we want to keep track of the different means because they can change after filling out the missing elements. Hence, before we take care of all the individual NaN elements of the array, it's a good idea to store the means of each column. In the next cell, we can use indexing to check the mean of the first column. The result is 2050.25. If we look towards the dataset we displayed above, we see mainly 1000 and 2000 as elements of this column. Hence, this mean seems reasonable. After checking this, we'll repeat what we did last time and choose a filler value greater than the maximum one in the set. Then, we'll re-import the dataset with the filler in place of all the missing elements. Now that we're all caught up, let's briefly elaborate on why we stored the means for each column. For starters, let's display the filler value we use for every missing element in the array. We see that we're substituting every missing element with 64,002. This value is roughly 32 times greater than the mean of the first column, which was 2250.25, and this makes the filler a huge outlier for this column. Next, we can use the mean function to find the average value of the first column of the dataset with no missing values. We'll use slicing to indicate we're only interested in the column with index 0. Finally, we'll call the round method to stay in line with the rounded values we decided to use earlier. The output we see is 4,263.25. This number should represent the average value in the first column. However, this average is distorted due to all the missing values we've substituted with our filler. To get a sense of how big of an impact this could have on the result, let's display the mean of this column prior to filling out the missing values. The output is 2,250.25. This is close to twice smaller than the current mean of 4,263.25. This staggering difference could result in extracting misleading insights from the data. Luckily, we can use NumPy's where function to substitute the filler values with the associated mean for each column. All right, so NP_where creates an array following a very simple rule. We define a condition, and if it's met, we assign one value, and if it isn't, another. The way we'll be using this is very intuitive. We'll go through a column, and if an element is equal to the filler, we'll set it equal to the mean of the column. If it isn't, we'll set it equal to itself. This way, every non-filler value will remain unchanged, and every filler will now contain the mean of the column instead. The syntax for this is very straightforward. We set the first column of the dataset equal to the output of NP_where. Within the parentheses, we define the condition as an element of the array to be equal to the filler variable. Then, we write a comma and set the value we want to use instead, which is the mean of the first column in this case. Afterwards, we write another comma and add the value we use when the condition isn't met. Here, that's just the individual element we're comparing to the filler. Let's check if this submission has worked. Unlike last time, we can't simply check the number of missing values, since they were all filled out before we even began substituting. What we can do instead is find the new mean of the first column. We can just copy the code we wrote a few lines above and see that the new mean differs from the old one. In fact, the new one is identical to the mean prior to filling out any missing values. This is no coincidence, since whenever we add the mean of a set to itself, the mean of the new set stays the same. For instance, let's take the set of numbers 1, 2, and 3. Their sum is 6, so the mean is clearly 2, and if we add it to the mix, the new set becomes 1, 2, 2, and 3. The sum is now 8, but there are 4 elements, so the mean is once again 2. The exact same thing happens in each column here because we're substituting all the initially missing elements with the mean of the set to create a new larger set with the same mean. For this reason, this is the most simplistic yet logically sound way to fill in missing values. Fantastic! Since this substitution worked out great, we can generalize this transformation for all the columns of the dataset. To do this, we can use an iteration that goes through all the columns of the array one by one. For instance, take a for loop which goes from 0 up to the index of the last column of the dataset. Conveniently, we can call the range function here and use the shape attribute of the array to get the number of columns in the dataset. Hence, the syntax looks like this. For some variable I in range and within the parentheses, we write the name of the dataset variable, .shape. After shape, opening square bracket, 1, closing square bracket. We write 1 in here instead of 0 because 1 gives us the number of columns, while 0 the number of rows. We end the line with a colon and move to the next one. After indenting, we simply paste the code we wrote for substituting values in the first column. Then we switch out all the zeros for i's. This ensures we'll be iterating over each column and changing the mean appropriately. Fantastic! After we execute this loop, we will in fact substitute every missing individual element with the mean of the column it is in. Of course, we could have used something different than the mean, like the weighted average or a mode, for instance. In the given circumstances, it felt like this is the best fit. But in general, it's up to you as an analyst to decide how to fill these up. Finally, it is important to remember that NP-where can be used to replace non-missing values as well. For example, if we don't want to have negative values in our dataset, we can simply set them all to 0. To do this, we can copy the code from earlier and change the condition to less than 0. Then change the value we're passing from the mean of the column to 0, and we're set. Of course, we shouldn't forget to designate that we want to keep working with all positive values in our dataset by using this expression before closing the parentheses. Okay! I hope you enjoyed what we learned so far in this section. Dealing with missing data is an everyday activity for every analyst or researcher working with large amounts of data. Now that we've taken care of the missing values, we can focus our attention on other preprocessing techniques. In the next lecture, we'll explain why we sometimes need to reshape arrays and how to do it most efficiently. Thanks for watching.